Hello everyone, please tell if you can hear and see me. Uh, we are continuing at the same spot where we left off the last time, so the presentation goes on from where we finished. We are still somewhere in the stationarity. What we did the last time, we covered formal testing and formal tests of stationarity and non-stationarity, the ADF and KPSS tests, and considered a few examples, and then also in the practice session. So now we are continuing, and we are about to get closer to modeling, because what we are doing in general, we are getting to know how to deal with special properties of time series, that is non-stationarity, for example, for many economic time series, how to deal with them in modeling, and how we can use that. So what we learned so far basically is that a lot of economic time series are non-stationary, and then the logical question would be, so what's next? The important thing is that for models, for not all models, but for many models, uh, we need stationary time series. And in our course, we are going to work uh, only with models that are applied to stationary time series. Yes, we are going to use the initial data from non-stationary time series, but we are going to do something to make them stationary, and you already saw what we can do. Uh, if you are interested in models of non-stationary time series as well, and that is also very useful, but this is a little bit already more advanced level, and we don't have time for that, because if we had a longer course, for example, for two modules as standard econometrics, then next logical step after stationary time series would be models of non-stationary time series, one of many possible steps. And if you are interested in that, there is a good selection of topics about non-stationarity too in the online course that I suggested for you. Have you seen the announcement on the Padlet about the massive open online course on macroeconomic forecasting? Yes, great, thanks. So if you had not before, and you don't understand now what I'm talking about, go on Padlet. There is in the important things some big red post about massive open online course. EDX and International Monetary Fund created macroeconomic forecasting course, and studying it, your self-study of this course is a part of our course. You have to study at least, well, by yourselves, at least half of it. How well you did on that? Well, we are not going to have a quiz on that or a test or something else, but I will see how well you did in that from your project tasks, firstly. And then also, if you're interested in non-stationary time series, for example, if your maybe term paper or your future graduation paper, you see already that it is going to be somewhere around macroeconomics and working with macro data more, uh, then that online course definitely worth for you to study, because there are some essential macro time series models there. Unfortunately, we don't have time for them. Okay, but now more about stationarity and using stationary time series in models in our course. So, what shall we do with time series when they are non-stationary, but we understand that we want them stationary? A lot of things can be solved by applying stationary transformations to the data that we have. And this is what we are going to do right now. This is the topic of today's lecture. And then when we learn how to do that, we can apply simple time series models already to just one time series. And this is the topic of our next classes. It says week 3, 4. It's actually 4 and 5, maybe a little bit longer. And this is the main topic of your project task. So linear modeling and prediction. of just one time series. That is why we call the models of that type univariate. That the ones that use only one variable at a time, one time series. It uses many variables because we use present and future and past values at the same time in one model. But the time series is only one. That's why it's univariate. Mhm. But now stationary transformations, and not all of them. There are a lot of ways to transform time series to make a non-stationary dynamics to look like stationary, or maybe to be closer to stationary, and so on. We only covered the very basic ones, the ones that you need to deal with the data that you chose already for your projects. In most cases, it is going to be enough. In those that are not going to be enough, I will tell you what to do. Don't worry. Uh, so yeah, once again, a lot of important time series in economics and in economy related are essentially non-stationary because of the economic growth, because of the cycles, because of the trends, because of the policy interventions, and so on. There are many reasons for uh, economic time series to be non-stationary, non-stationary at least in mean level. So at least for the average level of time series to change significantly over time in different manner, not necessarily in the manner of trend, but something else maybe like structural shifts and so on. Well, it says earlier today, it means in this presentation, but do you remember maybe, have we seen an example of stationary transformation already? Well, the answer is obviously that yes, we have, but well, okay, so since it's been almost a week since the last class, let's not spend time on that. Just recall that example. You saw it already at least 3 times in our classes. This graph of the United States import of goods, and the description of the data here says that it is percentage change. The values of these data are annual, so each year there is only one single value. That's why annual, and it says percentage change, meaning that by default the percentage change is in this year based on the previous year. So how many more percent uh, import of goods this year is more than the last year. This is what the percentage change means. There could be also percentage growth, then it would be plus 100%, but essentially it's the same. So whenever this thing is negative, we understand that the initial import was lower than in the previous year. Whenever it's positive, we understand that this year the import of goods is higher than last year, and so on. So you remember this, I hope. There are two important questions. So what is the transformation here that made something that was non-stationary stationary, and how does the initial import series look like? So there is percentage change, and well, it is already obvious that the percentage change is the transformation. This is something that transformed time series that used to be non-stationary into stationary, probably. And you remember from the practice sessions that yes, we tested that and we discussed that essentially and analyzed it visually, and then even considered formal tests and made the conclusion that yeah, we don't have any reasons to think that this thing is not stationary. What do you think the initial import series looked like? You can unmute yourself and say. Yeah, so that was import of goods measured in some monetary value, probably in dollars or something. But what if we plotted it? What it looked like? The graph of it. What are the distinctive features of the dynamics of the initial import? upward trend. Yes, let's discuss later which one, but why upward? First of all, why upward?
Ну, потому что изменения у нас положительные обычно.
Yes, thank you. So most of the time, as I said, whenever the percentage change in this year compared to the previous year was negative, there was a decline in the initial import. And whenever that thing is positive, there was growth in the initial import. And you see that here's the zero line. Most of the time, the import was growing. Yeah, the percentage change was kind of stable. It remained somewhere most of the time between 0 and, well, 12% probably, well, 15, yeah, between 0 and 15, even maybe between 5 and 15 most of the time, approximately. So it was growing. On average, I would say that the average growth here is something like 8% or something like that. I'm not sure, maybe even more, higher. It's not important. It's obviously positive because there are only very few points with negative values on this graph. So it was growing. And definitely, yes, there was a trend. There was some declines. They were not too deep. Sometimes there was almost no growth when the values were close to zero. Sometimes the decline was very minor. There was one after the crisis of 2008, 10, 8, 9. There was quite a deep decline, something like minus 12% over 1 year. That's too much, but then it was quite a rapid growth after, so it was restored probably. No, the trend was quite persistent. It wasn't change in the trends. It was growing, growing, and growing pretty much in the same manner, except for this one decline here in the crisis. What kind of trend? This is also important. So yes, upward trend, but something else about the trend. Yes, trends are non-stationary. Of course, trend is non-stationary. What kind of trends do you know? Let's say, if we say that it's upward trend, it's already about sustainable growth. So it's not about cyclic trend, not about seasonality because it's annual data, not cycles, uh, not shifting something. I know that you know because we discussed a similar situation with another sample, and you gave the right answer in the practice session. If you had to draw this thing over time, what would it be? Okay, is it growing? Would it be something like that grows like this? That's 2008 probably. Does this look reasonable?
Нет, у нас слишком большой разброс. У нас в начале, как минимум, он должен резко вырасти. Ну, это не линейно будет.
Those are
У вас
details.
линейно это нарисовано, а это не линейно.
Yes, thank you. So that's what I'm asking for, the type of trend, the type of growth. So it's not cyclic, it's not shifting. There's also something rapid in the beginning, yes. Quite similar to this decline in the crisis. There should be something like this in the beginning, yes. So something like this, yeah. But without declines after. But the most important thing about this is that the trend is not linear. Because if something grows linearly like this, what is the percentage change? The percentage change, for example, if it started here at value 1 and the next time period is +1, which is 2 here, this is linear growth, and then it's 3 and so on. What is the percentage change between these two values? From 1 to 2.
Ну, 100%.
Yes, that's plus 100%, dear economists. What is the percentage change here? From 2 to 3.
50.
Plus 50, yes. Then plus, and so on. So if you apply percentage transformation to a linear, something that grows linearly, the resulting percentage change will not be stationary, it will be declining. Because as the basic level grows, the percentage change declines because the same, right? What would be the next thing from 3 to 4?
Ну, 33%.
Yeah, something approximately. So 1/3 and so on. So the percentage change of this type of growth would be declining because the same absolute change, the same absolute growth has less and less share in the accumulated value of the level. And what we have here is that approximately the percentage change stays the same. It's not, of course, it's not the same, but it is stationary. That means that on average, right? So the conclusion about the time series that we made, on average, yeah, I'm hiding the plot here, sorry. On average, the percentage change doesn't change much. Yeah, so it is fluctuating, but around the same stable over time level. That's the definition and the property of stationarity. We concluded that yes, percentage change looks like it's stationary in mean. There are some deviations, but they are only short term, and most of the time it stays in one region, so the average level doesn't change much. So there is some average level of the percentage change. There are some deviations. It is higher, sometimes it is lower, sometimes that creates fluctuations, but most of the time it is somewhat the same. Well, between 5 and 15%, let's say. So what would be the initial series then?
Ну, экспоненты тогда.
Yay, exponential growth. Thank you. Something like this. The basic, that would be the average, the trend component of that thing that grows with constant, exactly constant percentage change, right? And then there are some fluctuations above, below, and so on. There was even some decline in 2008, and so on. But most of the time it grows. I'm not picturing all the distinctive features here, just maybe this. It's not 8, it's even 10. There was rapid growth in the beginning, but you won't see it much because it was in the very beginning when the level was not so high 30 years ago. So that time it was rapid, but on the when you have this rapid growth over 30 years, it is lost somewhere there. So you won't see it as this big jump here. Okay, so this is what it does. And those of you who gave the answer to the exit ticket last practice session were correct. The most common way to kill the non-stationarity of GDP, for example, over some pretty long period of time, and in a developed world, it is of course important, but in general, on average, yeah, the most commonly used stationary transformation to kill non-stationarity in GDP is percentage growth. Exactly because of that. Because, well, economies grow on average exponentially. If you close your eyes and don't notice all the like shifts and crises and so on average over a longer period of time, the growth is exponential. And the way to kill it and make it look stationary is to apply percentage change. If you apply a linear transformation, it might not be enough because you cannot kill exponential trend by taking absolute differences. They will be growing themselves. Then you can apply it again, but there is no guarantee that it's going to be enough. If the trend is truly exponential, no amount of differentiation will kill it. You know it from mathematical analysis. No matter how many times you take derivative of exponential function, it remains exponential still, right? Okay, no, we will see it. So there is some analogy between taking stationary transformations and differentiation over time. So we'll have to transform our data from being non-stationary to stationary ones to be able to model them, at least to apply the models that require stationarity. And what transformation should be chosen really depends on the type of non-stationarity. So some types of non-stationarity cannot be killed by any transformations. They can only be accounted for in models, inside the models. The transformations that are going to be used, this is very important now, and this is going to be important for your future analysis in your projects. So the transformations that are applied to the data prior to modeling, before we model them, they exist to handle trends. Trends in mean, sometimes trends in variance, but not often. So mostly trends in mean before you try to model the data. So sometimes there are transformations that help to kill not only trends that are sustainable growth or decline, like in the example that we saw, but also, for example, seasonality. But it is better practice to apply seasonal transformations inside the model so that your model accounts for seasonality, because especially if it is a predictive model, for example. Well, but there are options. And definitely such things as structural breaks and trends in variance, that is heteroscedasticity, they have to be dealt with inside the models. Because you cannot transform the data to kill non-stationarity that is caused by structural break. Well, you can just say, okay, this on average that time series jumped here like by factor of 2 and then remained on that new level. Let's just delete it. But then what? You don't know anything about why it happened, whether you should expect it again, or what is the exact change that happened there, and so on. What caused it? Well, one way to transform the data to account for structural break, if your data allows for that, would be to cut the older values before the structural break, if it happened quite a long time ago. That's it. No other transformation can be applied. So what we are considering today is about this: the transformations that are applied to the data before modeling, and they are applied to kill trends in mean. Most of them are applied to kill the trends that are sustainable growth or sustainable decline. So linear growth or exponential growth or other types of growth. And that special type of non-stationarity that we call unit root. We don't know yet what it is, but we know that ADF test discovers it. That is a situation when there is not one particular trend, but something like that looks like a trend that can be there in the dynamics of the time series for some time, then change, and so on. You might have heard about special type of the unit root, which is called random walk. That is exactly unit root, but just one kind of it. Okay. The first type of the transformations that we are going to see, and well, the only one today actually, is the so-called detrending transformations. And there are many kinds of that, depending on the type of trend. As we just saw in the very brief example, one transformation can be applied to exponential trend, but it cannot be applied to linear trend, because then it will not result in a stationary time series, and the opposite. If you apply something that can make linear trend stationary, if you apply it to exponential trend, it will not cause, it will not result in stationarity. And again, the same idea as with the testing. Essential meaning of transformation is crucial, especially when your purpose is not just to look at the pretty graphs that look like stationary processes, but also to model the data. And if you apply transformations to the data that are meaningless, you can achieve something that looks stationary, but then it is pretty much impossible to use that in models, because you are going to model something that has no meaning. And there are many examples of such unfortunate transformations, well, very unfortunate. The most obvious one, for example, is to apply percentage change twice. When you see something that is already measured as a percentage change, and you apply another percentage change to that. So percentage change of percentage change, mathematically, that makes sense. Essentially, well, how would you interpret it? It's like, well, something very hard to imagine and hard to interpret, especially when you model it or want to explain what is the meaning of your marginal effect or the meaning of your prediction and so on, of such a strange value that is percentage of percentage. Another thing is when you try to apply percentage transformations, not necessarily percentage change, but something percentage related to things that changes signs. And when you have to take percentage values from of how many percentage percent a negative value is of positive value, and then the opposite, so it just might make no sense. And another thing of meaning and of basically meaningless transformation, unfortunately, it is still often used, and you might see it even in something like not really maybe science-based analysis, in maybe some popular explanations about trends and so on. Compare percentage changes and deviations from trend. What a deviation from a trend, we will see soon. But basically, if you see that something grows linearly or exponentially, and you imagine, okay, those, on average, the trend is this, let's just take as a stationary transformation what is fluctuating around that trend. And well, it might sound good, the result might even look like something stationary, but then unfortunately it makes no sense for modeling. Well, we will see it in practice session. But let's try to compare what it means by percentage change and what it means deviating from a trend. So percentage change, we just saw it in an example, empirical example of how it looks. Mathematically, it's pretty easy. If we had original time series that is xt, is it visible? Yeah, it should be null.
Yes.
xt, which is something potentially stationary, non-stationary, doesn't matter, but something that say can be well, can make sense in percentage. If we compare how much, how many percent current value is of the previous value and so on, then the percentage change is just this. Well, if you want to measure them in percent, then also times 100%, but usually we don't do that. We just write it down like this and say that we call it percentage change, or the what is another term to call it? You should know it. So one way to call it would be percentage change, even if it's not measured in percentage, but just as a share from 0 to 1 or from -1 to 1 or whatever. It might be even more than 1 easily. What is the other way to call it? Hello, macroeconomics, national statistics, labor statistics. Yes, thank you, it's growth rate. And the crucial term here would be rate, because there's always also this thing, which is very, very close in meaning, and right, and it also is related to percentage. It's just that it is not based around 0, it is based around 100 or around 100% or around 1. This would be just growth. Without rate. But when we say percentage change or growth rate, this is what we mean. Sometimes just growth, then this. Well, basically just subtract 1 from this and you will get the rate. It's quite easy. So the advantage of using percentage change as a transformation and when it is applied to such data as, for example, GDP, or as we saw, something like macro related, like import of goods dynamics, or also something like population dynamics. What else? Something that could grow exponentially. We saw that electricity generation data and so on. So something that is growth related, economy growth related, long-term economy growth that causes exponential trends. Then applying percentage change, one period percentage change. One period means that we compare the current value with the previous period exactly. So this year compared to previous year, if the data is annual, divided by the previous year. So how previous year's value, how many more percent the value current year is than it was the last year, and so on. This is very convenient when you are trying to evaluate, well, the growth, of course, obviously, the growth or decline, whatever is going on there in the data. And when you are going to evaluate short-run effects of the policy or of some ongoing tendencies, maybe of some random events, or are they not random, but just other events other than policy or random, that took place in nearest past and so on. Because the values are showing the relative dynamics of nearest future compared to the nearest past, just one period ahead. And when we consider the whole trend over a long period of time, saying that, okay, on average, this thing was behaving like this is the dynamics of it, it looks like exponential function or linear function of time, then it shows the long run tendency. And to be able to evaluate it, you need that long period, all of it, of that long period over which you are measuring that value. And it can be used in some long-term, long-run models, or in some ways, some attempts to identify or define long-run effects or some consequences of shifts in longer period of time when we want to see whether the whole trend changed or not, and so on. But not in the determination or the analysis of short-run effects and short-run predictions, because the predictive properties of such things are very, very poor. So basically, we don't do them in short-run predictions. And the models of stationary time series are all about short-running effects. And this is very important. Note here, remark. So the long-run trends of time are not used in practice anymore. You can still see them maybe in all the textbooks or in some not very good papers and studies as examples of models when the dynamics is explained as a function of time plus something. But in real practice, in real analysis, they are not used anymore. They are used as the basic components of some models that are used for testing. For example, trends of time, you can see them in tests for stationarity. Then a model that is based on a trend of time is used to run ADF test, not ADF, sorry, is used to run the KPSS test, for example, but only for that, to calculate the statistics and make the conclusion about the null hypothesis. That's it. The model itself, it has no essential meaning and doesn't say anything essential or valuable about the meaning of those tendencies and those stationarities and non-stationarities, only to test the hypothesis. So when something is growing persistently, linearly, or exponentially, or in some other way, those transformations like percentage change or absolute values differences, those transformations that compare the most recent future values with the most recent past values are a lot better, and this is what we use. So these are the most commonly used types of transformations of this kind. We discussed the growth rates now, or the percentage change. That's the same, pretty much. The most commonly used in theoretical models transformations is the so-called difference transformations. It doesn't mean that we have to use that in practice, and in practice they are used as often as anything else. But in textbooks, this is the first thing that you would see, because this is a lot easier to analyze in theory. That percentage change. Percentage changes are not usually used in theoretical models, other than macroeconomic models that are not combined with statistical techniques. So for them, nice properties like additiveness and stuff like that, difference transformations are used. And then there's something that makes peace between difference transformations and percentage growth, that is called log differences. It is very commonly applied in macro to macro data in macroeconomic analysis, and it is very, very popular in financial econometrics and applied to financial time series, and there's reason why. So for many of your practice your homework assignments, many of you would end up using this transformation. But why the difference transformations are the basic ones and most commonly used in theoretical constructions is that because all the transformation of those kinds, they are based on differencing. So let's deal with them. Well, before we get to the examples, probably some notation. If we have a time series that whose values are xt, tb in time, of course, as usually, and x other values. Doesn't matter now what time series that is, just time series that is stationary or not stationary, doesn't matter. This is just about the definition. So the definition of the difference transformation would be basically this: current value minus the past value. I'm sure you already saw this at some point. This transformation we call the first difference. We denote it as this sometimes. Sometimes you will see this definition, but well, it is not a good practice to combine that mathematical things that we use in the analysis with statistical. So this is the preferred notation for it. Sometimes you will see also equivalent notation like this with another symbol. Well, that depends on the textbook, but in most textbooks and papers you will see this. So delta, that capital delta stands for differencing operator. That means that we are taking the first difference of it. That's just the definition. Then, yeah, that would be called the first difference. Of the time series. Why the first? Because this takes the difference once. If you apply difference twice, then it would be the second difference, and so on. Short notation for that would be this. Does it look familiar? Have you seen it somewhere before? Maybe in macro class in statistics somewhere. Okay, probably not. Well, yeah, that's the same kind of notation as you use in mathematical analysis for differentiation, for differentials. The idea is also the same. The difference is that you now differentiate, somewhat like differentiate with respect to time, but the time is not continuous here, so you cannot take the point change here. The change is kind of point, because point is from going from moment in time, from moment 1 to moment 2 to moment 3 and so on. So the idea is the same. In the theory of stochastic processes, it's exactly the same, and basically in continuous time you will get to the differentiation with respect to time. But here it's just like technical thing, and it is better to think about it not as differential and differentiation, but taking finite differences. And it's better to think about the data at this point, because our course is really about thinking about data and applying very basic models to data. And yeah, if you think about those things as differentials, it's not gonna make you any good, unfortunately. But if you want to really study the theory of time series, then yes, you can start doing that. Now, if you continue to expand this expression for the second difference, it is going to be something quite ugly. Right? So this is just applying the definition one by one, the definition of the first difference one by one. So the second difference is the first difference of the first difference. The first difference is this. The first difference shifted in time back is this. The first difference of the first difference is this ugly thing. And when you keep expanding it, none. So this is how the second difference looks like in terms of the initial time series. Please never, 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 never confuse it with this. It is not defined like this. No. And to those of you who will make this mistake in quiz, and there's going to be this question about this, I'm going to subtract additional points. So please try not to make this mistake. Do your best. Well, you can imagine how ugly this thing would be if you apply it and make it the third difference and so on. So that will look even uglier and so on and so forth. So we don't have such aims to expand all of them, but it would be good if you try to imagine how it looks like. So you can try do it on your free time. It will not be so hard, but it is important to understand what it means. So when we discuss the first difference, this one, it is obvious. So how much the time series changes in absolute value, not in absolute value, just in the basic value, not in percentages, in the same units. So the units of this thing, of the first difference, remains the same. This is why we say that the essential meaning of the transformation is very important when you apply to it. The differencing transformation would only make sense if the units of the initial level value can be preserved. If it's something that you cannot subtract or add, then, well, why bother? For example, if your initial series is measured in percentages that are percentages of something different base. So for example, it's percentage of some value that changes also over time. Then it makes no sense to compare them in differencing transformation. Or if your initial time series, for example, is a probability, which has no units basically, or it's some utility that also is unitless, and it's not clear what this difference would mean. So what does it mean that it grew or declined by this difference? Well, okay. Let's try to see an empirical example. It's not really empirical. This one is empirical. Yes, sorry, I thought that it is about simulated data. No, this one is not simulated data. So this is an example that we saw something like that, but in a different country. You remember that from the first practice session, we saw that CO2 emissions in Europe, I believe, and there was something a lot different over the pretty much the same period of time. And this is the CO2 emissions in Morocco. What do you think about stationarity of this thing, of the initial one, the first half, the levels? Non-stationary. Why? Yes, upward trend, sustainable growth, definitely non-stationary in mean done. No formal testing is required. Yeah, that should be really easy. And then you see the plot of the first differences. This is it, first diffs. So by how much it changes. So the units are the same. It was in megatons. It remained in megatons because this is just the difference. How many megatons more this year as compared to the previous one? you see that most of the time this thing is positive, so there were only very few declines. 1, 2, 3. Most of the time it grows. So the logic is the same as with other changes. Whenever this is positive, the initial series grows. Do you think this transformation made it stationary? Does it look stationary? The second one, the transformed data. Yeah, the first part, which is the first part, the first half you mean, right? So earlier than 90s. Um, what's wrong with the second half?
Там дисперсия больше.
Okay, so when the variance is higher, it doesn't mean that it is not stationary. The important thing that it is stable.
Не, подождите, там же должна и это... Стоп.
Стою, не стреляйте.
Подождите, там средняя, значит, дисперсия, и еще это, которая, типа...
Yes, the covariance, we are not talking even about that because no stationarity tests and judgment about stationarity tests for covariance stationarity. Most of the tests that we apply only test for stationarity in mean. Some of them test for stationarity in variance, and that's it. Usually, if something fails, it fails on the level of the average level, sometimes on the level of the variance, and we even don't have to go into the covariance or something. The important thing is non-stability. So, and recall, well, let's go here somewhere. Where? Yes, this is the important thing. So most transformations that we apply to data, they are applied to deal with trends in mean, so trends in average level. They are going to kill non-stationarity on average. Sometimes applying a transformation will cause other troubles, like in this example. Yes, it did kill, obviously, it killed the trend. There's no sustainable growth anymore. And it seems like this resulting thing is stable on average. So the average level here in the first part looks, well, it is a lot more stable than the second half, but the average level seems pretty much the same. It might have changed. It is not visible just from visual analysis. Maybe formal test is required whether this thing is stable on average or not. But it clearly created some fluctuations in the variance. Yeah, so the first part might look as stationary on its own. The second part looks stationary like its own. The whole thing looks stationary in mean, but maybe some additional testing is required, but it's definitely not stationary in variance anymore. Not anymore, but just not stationary in variance. Before there was non-stationarity in mean, we could not even consider variance. Now, when the mean is somewhat stable over time, we can think about variance, and yes, so, well, applying differencing transformation created non-stationarity in variance. That happens, why not? It doesn't mean that we cannot use this data in model. Maybe we can. Maybe it is okay with us to cut the older data because we have almost 30 years here in this part of the sample. We can use just that when the variance is already okay. If we are only interested in the dynamics of the mean, or we crucially want to use all the data, we can use it still because it looks stationary in mean at least. For many models, this is already enough. But clearly something happened here in the 90s. And well, you can guess what happened there. You can also compare it with the same type of data, but for Europe. and guess what happened there. But yeah, also notice that when you see this this transformation, which is supposed to make things stationary, but it doesn't seem that it does eventually. That something happens really here, and maybe the trend changes. It looks like linear at first, but then, well, yeah, you see that the growth here is a lot more stable than after, and it seems that the average level also changed. So it might be that stationarity tests will discover some non-stationarity even this. But yeah, well, this is one of the possible ways to transform it. Maybe another transformation would be better. So the same logic and the same idea that same ideas that we used to test for stationarity of this initial data applies to the data that are transformed. But we also use some information that we know about the data from the initial data, of course. So we try to use all the information that we have. Going back to the definitions, this is the definition of the first difference applied to the data, denoted as delta again, and this is the definition. This is the notation that we are going to use in this course. If you see something else in other courses or other textbooks, then don't be confused. Just follow the notation. It's okay. First, why first? Because well, this is how it is defined. The first difference. You take the difference once. And then the general definition of the difference transformation is the difference of order p, or the pth difference, then it would be the second difference, the third difference, the difference of the order 4, of order 5, and so on. This is, it's defined iteratively. The difference of order p is the first difference applied to the difference of order p minus 1. Then, very quick question. What's this? That's 0. Yes. That's just identity transformation. So technically, if you think about this thing as a linear operator, and it is a linear operator over the time series, then you can also consider something like this, for example. It's also valid. Why not? But we will not. Even this is not required usually, because if you follow that definition that I just gave you, then you will not ever face the difference of order 0, of order 1, and something else. Now another example, but with a simulated data. Yes, the resolution is something strange. Yeah, so yeah, we don't have much time, unfortunately. Well, let's try to go faster. Now see that this is simulated data. The original data in levels is something that grows over time. Obviously non-stationary. There's sustainable growth. We cannot say anything essential about it because this is simulated data. So something that grows. How grows? Well, something. And you see that here in the first difference plot, the bottom part of this plot, the red line is at the level of the average level of the first difference, and it is positive. And now a very important question. So we are not going to use VooClub for that. There's no time, unfortunately, but let's maybe try to give it some thinking. So I will give you now maybe a minute or something to think about it. Please do it on your own. And the question is very technical and quite precise. The first difference of some time series over some period, particular period. So this is not a theoretical property. It's just about particular data. So this is a particular time series data, and the average level of the first difference is strictly positive. So you have data, you calculated the average level of the first difference, it's positive. Does it guarantee that the level of the initial series grew over that period? Like in this example before, there's growth, this is the first difference, and then on average the mean level of the first difference over this sample is positive. Does this guarantee that that thing grew? For example, if we saw only the second part of this plot, on average this thing is positive. Does it mean that the original thing grew?
Ну, вообще нет. Можно там
So there are
какой-нибудь пример привести.
few answers that no. Why?
Нет, ну вот смотрите, мы знаем, что чтобы компенсировать падение 20%, нужно вырасти на 25%. Вот.
That's not about percentages, that's about first differences. Yes, that's the crucial here. The first differences are positive on average, not percentage growth.
Ну тогда, конечно.
Yeah, I see your logic behind the answer no and the discussion about the percentage growth, and you are absolutely right. And then, yes, so please, this is not the first time. I'm not sure whether it's my way of talking, my way of writing or something, but guys, I am like waving hands, all sorts.
Не, первая разница, конечно,
please,
да, это гарантирует.
Lips moving, still talking, Roman. Thanks.
Да,
please be very attentive to the instructions on this course, especially if English brings some trouble for you. This is very crucial. That's already been problem in multiple situations with us. Yes, now it's about positive difference. Now please go on. What did you want to say? Sorry for interruption.
Я хотел сказать, что это гарантирует, конечно.
Yes.
Это просто абсолютное изменение. Это, если мы их просуммируем, мы как раз получим то, к чему придем.
Because what we have, that the first difference is this. And the average of this thing, by definition, is so this is the average of the first difference. Quick question again, why minus n minus 1 here, and why from t at 2? Oh, this is an easy question. Okay, later then. And then let's start to open it up. So n minus 1 remains here, it's okay. But the summation, yeah, and well, yeah, okay, let it be n. And you see what happens here. This is exactly, no, sorry. This cancels out, this cancels out, something else is also cancelled out there. And what remains? This. Exactly, because this is, as you said, the change in the same units, so this is just a difference. between two periods. When you add up difference in two sequent periods, you get the difference over two periods, and so on. So if it's positive, then it's of course possible only when the whole time series for the whole period grew. Same with exact zero, same with exactly negative. And you are absolutely right. This does not apply to percentage change, because in the percentage change, uh, the basis of the percentage is always different, and sometimes one huge positive change somewhere in the very beginning cannot be covered by a series of many negative percentage changes over the periods, future periods, and on average, the percentage change could be negative, for example, but overall the time series would grow because of very few but significant percentage changes somewhere in the past. Well, that's it, because it's not additive transformation. And yes, just difference in transformation is additive, and it's going to be. Let's try to see how it works. So imagine now this, like, what if we had the same differences now? It is a little bit strange exercise, but notice the difference between these two plots. See what changes. The differences are the same, but they are shifted up and down by some constant value. And the higher the average level of the differences is, the more sound is growth, of course, because there are more periods when the time series grew, right? And we know that from this very simple derivation, that the mean level just shows the average change over the whole period, additive change. And now see what happens to the original level of the time series if it had the same differences, but the mean level of the differences is lower. When it gets lower, there appear more and more points that are negative, so there appear some periods of decline. The range of the original level also becomes lower. The trends becomes more volatile because of the changes that sometimes are closer to zero, sometimes are negative even, and so on. And the moment when it reaches zero on average, the first difference reaches zero on average, the difference is quite minimal, but still, since it's a little bit but strictly positive, there is growth. It's teeny tiny, but there is distinctive growth. And when it becomes negative, it changes to decline immediately. So only looking at the original levels dynamics, you can already judge about the average level of the first difference, whether it's negative or positive. And same, but in the other direction. And now, yes, so now the first difference is always negative, and there's just sustainable decline without any growth. Sometimes it's close to almost zero decline, but still it is a decline. So it's always declining, and quite a lot on average. So to sum up the information about the differences transformation, so it is important that the difference transformation, it preserves units. What it means, then we saw just for that Morocco data, megatons, they remain still megatons. They don't become something else like percentage or without units and so on. And if you apply even second difference to that, it will still be megatons. It will be just change in change, but still measured in the same units. And this only makes sense if the original units are additive. If they are not, then, well, the whole transformation might not make sense. Mathematically, statistically, it still can be used, but it would be hard to interpret it. And because of that, when the units are interpretable like that, when they are additive, the first differences are very easy to interpret. Unfortunately, the first differences are not enough, not always enough to kill, and often not enough to kill non-stationarity, kill, well, quotation marks, to make the dynamics of the time series, of the transformed time series, to look stationary. And then we can apply higher order of differences, like second differences, for example. And then they are already harder to interpret because change, that's wow. In practice, actually, sometimes you can see second order differences to be used in practical modeling. And higher orders, well, almost never. Well, like never. I've not seen it for years already in practice. In theoretical models, yeah, easily, no problem. But in applied analysis, no. So if you are applying differencing transformation to your data and you see that first differences is not enough, but still it makes some sense maybe to consider second order differences, why not? Maybe it will be okay to use second order difference. But if you applied second order differences, it is still not enough to kill non-stationarity. It is better to switch to something else. And by something else, we mean the percentage change or the growth rate. We just saw it. This is the definition. Uh, the property is that this change is scale free. So no matter what was the original unit of the time series, it is killed. So it is either in percentage or just scale free. Well, if you wanted to measure it in percent, then multiply it by 100. But usually we don't bother. And often it kills non-stationarity better than differences, exactly because of that. And also because, well, this statement applies to economic time series or economy-related, growth-related, especially in macro data, for example, or in finance. But sometimes it makes no sense, unfortunately. First of all, it's not additive, so you cannot add them up. And this statement about that average level of positive average level of first differences guarantees the growth overall, it does not apply anymore to percentage change because it's not additive and because the basis is all the time different, this one. And because it's scale free, sometimes it's even harder to interpret than second or higher order differences, unfortunately. Especially when the units of the original time series are not very well interpreted. So, yes. And the last one that we are going to consider today, and we are going to finish at this. Yeah, we have 5 minutes, so it's okay. The so-called log differences, same term log returns, and the same term log growth rate or logarithmic growth rate. These are synonyms. The difference is that the log returns term, it is used for financial data. When you apply this transformation to financial data that are essentially prices or something price-like in levels, like for example index value or something like that, then you get the thing that is called log returns. Well, otherwise, this is not used. You can still talk about log returns of GDP, for example. Well, but it kind of makes no sense because uh, it will be you will be well understood which kind of transformation you used, but the interpretation of that transformed data as returns doesn't make any sense. So, for those of you who are using price-like data. Price-like data in your projects. That includes also CPIs and PPIs of different kind. This would be one of the leading transformations to make your data look stationary, but not necessarily. So you can try other things as well. For stock market data, definitely this. Nothing else, even don't bother considering. You will see in practice sessions why. So the definition is like this. So the log differences is the first difference applied to logged data. So you first take log of the original time series X, and then you take the first difference. Of course, the time series originally, initially must be such that you can take the logarithmic transformation of it, right? So it should be almost surely positive. Otherwise, makes no sense. And then you apply difference in transformation, or because of the well-known properties of the log transformation of log function, this is the same as first taking the growth and then applying log. That's why the name log growth. Well, for some reason there's also rate, but it's a little bit strange. Why? Because it's log growth, but there's a reason. So any idea, maybe someone knows, or you have seen this transformation already before, you should have in macro courses, at least a little bit. I'm not sure actually where you are in your macro sequence now, but at some point there will be something like that there. Do you have any idea why we call it rate, even though this thing inside the log transformation is not rate?
Ну, потому что логарифм от единицы плюс x это примерно x.
Yay, thank you. Last year we spent like half a class on this, and I have no intention of doing this. So if this thing looks not familiar to you, so please go back wherever you need to, mathematical analysis, macro, whatever, and remember this, because this is very important, especially for using this type of transformation and so on, for financial data especially. Well, this works only, of course, when x is close to 0, something like that. So it should be really small, not necessarily positive. Negative also works, right? How do you derive this?
Там есть замечательный предел. Вот. Из него следует.
Yeah, either
А
that
1
or
плюс x
Taylor
в степени
transformation.
1 делить на x, это в пределе дает, если мы возьмем логарифм, то мы как раз получим такое.
Yes, so by definition of what a natural logarithm is, and by that limiting property that gives you the exponential. Yes, that's right. Another way to derive it directly is by just Taylor expansion of the first order to log. But that's the same basis. Yes, you're right. Thank you. So why that is and how it is applied here, like this. So we know that the growth, if we subtract and add 1 here inside, we get exactly this. The growth rate plus 1, and when the growth rate is not high, not large in absolute value, then this transformation, this approximation applies here, and we get exactly this. So this transformation of the time series is almost the same, or approximately the same, as the growth rate or as the percentage change. That's it. That's why name log growth rate. It doesn't mean that, so whenever you see log growth rate, it doesn't mean that you have to take growth rate and log it, because that doesn't make sense. Because this is the growth rate, and if you log it, you might not even get defined values, because this thing might be negative. So when you see log growth rate, it means this. And it's called like this because of this approximation. So when rho is this we denoted it by rho. When is it small enough? How small? Well, that depends what considered small, and it depends on the acceptable error in this approximation. Well, those are almost the same. Well, this picture yeah, let's spend maybe another minute on the log transformation, and then we'll figure. This picture shows how small it should be. So you see that here x is between minus 0.5 and plus 0.5, and you see that this is already, well, the deviation is quite strong here. This is the red line is the error of that approximation, the difference between black and blue lines. The black line is just y equal x, and this the blue line is that log of 1 plus x. And here, when x is almost 0, they are almost the same. Here, the second part of it shows the closer range when it's between plus minus 0.1. So, well, yeah, when the growth rate, when the percentage change, this guy, is between plus minus 10%, plus minus 0.1, then yeah, we can say that log log growth rate is almost the same. The deviation is not high. When it's higher, then, well, yes, the error, of course, expands. The idea why this thing is maybe better than the percentage change, and it often used instead of percentage change, is that essentially this is a first difference transformation. So we applied logged transformation to the time series and then differences to the logged values. So this is difference in transformation. It is additive, and then the property remains the same as for the differencing. When it is positive on average, this the log difference, it guarantees, of course, that the initial time series also grew, unlike the percentage change. Well, this question we will answer then in the practice session. And there's a similar series of pictures. So you see, if we change only the average level of the log differences, how it affects the initial levels. See that the average level changes only very in a very small range, because essentially we interpret it as percentage changes, and the initial levels, it looks like exponential now growth. Maybe the second part looks more like exponential because this tail looks like almost a constant because it's so not considered as compared to the other values. And the moment when the average level of the mean level of the log diffs change from positive to negative, the levels dynamics change from growth to decline. Same idea as with the first differences. Yeah. And huge negative exponential trend. Oh, this is, yeah, I'm sorry, I'm delaying you. This is the last slide, and then a short link. Just a comparison of the percentage change and log differences. They are different in interpretation. Sometimes one is used, sometimes another is preferred. Overall, over data, if we compare in practice, in financial data, in price-related data, as I said, yeah, I think that's it. Log differences are preferred. In macro data, such as that are huge, low-frequent data like GDP, some other macroeconomic flow data type series, percentage changes are used because they are easier to interpret, especially when you have the situation when log difference cannot be interpreted most of the time as the percentage change because of the high values of those percentages. because the approximation doesn't work. But overall, they are close to each other. So both often kill non-stationarity better than first differences, and when the first differences are not enough, when the trend is definitely not linear, when it is something like exponential, something like that. But both show one period change, of course, and technically and essentially very close when the percentage change is small. But when it is large, then, well, when the time series is quite volatile and it shows low frequent values with potentially high percentage change over one period, a high, which means higher in absolute value than 10% in one period, then percentage change is better. But when it is possible, we try to use the log diffs or the log returns because they are additive. So that's it. And well, because of that, yes, log diffs are preferred to percentage change to kill non-stationarity, but not always. If you have any questions now, you can stay and ask. If not, then I am not keeping you anymore. I'm sorry for the delay. Next time we are going to have a quiz that will cover formal testing and stationary transformation. So please be sure to attend tomorrow's practice session because we are going to discuss stationary transformations there. Make some screenshot or something and please visit this link, or you can open it from the presentation from Padlet. And there's not a quiz, but a self wrap-up. You will be able to answer a few questions about the stationary transformations and formal tests. And they are going to be very useful for you in the next week's quiz, I promise. We're going to cover some of them tomorrow. Also, you can ask some questions there, as usual. And tomorrow we will start practice session from answering your questions from all those exit tickets that we collected. So see you tomorrow.